Well, welcome to week 4, that is, and we're going to be talking about efficiency and optimization this week. And those two things go together. The themes for today is that we're going to strive for efficient processes, improve efficiency. That's a benefit of technology, but we need to know what we're doing. There's going to be investments ideas like how do we invest in technologies that are going to serve our purposes. And often we think about efficiency in terms of just one item like water or energy. And I'm just going to introduce this idea of multiple criteria today. And then we're going to revisit that after we've studied energy and water a little bit more. And then we need to remember throughout this lecture and our work this week that efficiency is related to the process. It's not the goal for society. So in today's presentation, I'm going to define efficiency, give some simple examples, talk about efficiency of processes as an optimization process. Then we'll look at design and some multiple objectives, and then we'll look about, because efficiency is not the goal, what are we really trying to get to, and how can we get better outcomes and behaviors. So first of all, just remember from last week that the amount of net energy that we get out of a process, overall energy process, is related to the number of steps, and that after the efficiency at each step decreases what's available for use in the next step. This is just a quick review because it goes along with our definition of efficiency that we're going to use, which is that generally it's the starting material, the amount of product, and the amount of waste, and the efficiency is the product divided by the amount of starting material. So now efficiency can be high or low. It's just a ratio. And sometimes this waste that's going off is not bad. Sometimes having the right waste may be much more important than getting just the optimal amount of product. And we see that in chemical reactions and other things where we really like to get a good set of product, but some waste might be toxic and some might not. But I'm going to talk about some other examples of that too. Now, there's two types of efficiency that we're going to talk about in this class, and one is really the simple process efficiency, just like we talked about with the energy, the net energy, or that diagram up above it. It's something like total energy in minus the waste energy gives you the energy that goes to new growth, for example, of a plant or an animal, and this is the metabolism. So what's the efficiency of that metabolism? That's just a very simple process efficiency. And the overall efficiency, again, is just the amount of energy that's usable, in this case for growth, divided by the total amount in, and the amount that's not usable is the waste. Okay, now, another definition of efficiency is the overall efficiency, where we take into account how much machinery it takes to make a product. So we not only have the processes running, but we have the machinery that's required to make this product. And we're going to see this diagram several times, so I want to explain it once now and then come back to it a little bit later. So let's say we have machinery that runs process A, and it runs that at a particular efficiency of just this one process. There's a factor for that process. So the machinery for process A produces a subproduct that's A. And then similarly, the machinery for process B makes this subproduct. And then you need to have A and B joined together to make the final product. So just the basics of this is if you have too much machinery for process A, this is going too fast and you've wasted your investment in this machinery. Or if you had too much machinery for process B, same thing, you wasted having too much machinery in process B. Now, I'm going to go through a simple calculation on this that shows how this might work, and the little equations are given down below. But let me just say, what if we need a 2-to-1 ratio of A to B? We need twice as much of this as we have of this. But we have the same amount of machinery and they have the same factor for processing. So let's just imagine we have 10 units of this and we have the factor for process A is 0.5, and so we get 5 units per time. And we have 10 of this and a factor of 0.5 for this process. We get 5 per unit time. When we come over here, we get 5 of A and 5 of B, but we only need 2.5 of B to make this product. So we have over, this machinery is working well, but in the context of this overall efficiency, we've got too much of this. And we can correct that in 2 ways. We can increase the amount of machinery for process A. We do that, we'd have 20 of this making 10 units of A per time, and we'd have 10 of this making 5 units of B per time, and when we come out here we'd be able to make 5 units of product per time. So that's one way to solve this efficiency, is by increasing the amount of process A. The other way is we could decrease this. If we only get 5 out of here, if we only need 2.5 out of here, we could just put, instead of 10 units of machinery here, 5 units of machinery. We'd get 10 times 0.5 equals 5 per unit time, and 5 times 0.5, we'd get 2.5. We'd have the right ratio. So we'd overall have less machinery. We'd have the same overall efficiency. So this is the overall efficiency, and we're going to see some examples of that. And again, I'm going to come back to this in a little bit. But just remember, we're talking about 2 types of efficiency all the time, and I'll try to be clear about that. But if it's just sort of output over total input, that's a simple process. If we're talking about the machinery involved, then that's this overall efficiency. So let's talk about some simple examples. And I've got a little table here of a couple examples that you can read through. I'm not going to go through this point by point, because I'm going to explain stoves and water efficiency. But here's refrigeration. That's refrigerators in your home, a big use of energy. How would we calculate that? Water pumping and storage. I'm going to give an example of that a little bit. Wood stoves and cooking. I'm going to give an example. And then transportation. And this transportation one at the bottom really shows that transportation in the United States has so many objectives for our society that it's very difficult to assess this along any one dimension. So this isn't necessarily a good example of efficiency, but it's an example where just looking at efficiency of transportation, of getting from point A to point B, is not really the whole point about the transportation system. So let's look at some simpler examples. And one that you're going to be doing in lab is this efficiency of stoves. And what you're going to be doing is one variation of this and comparing your data across the whole class. But one of the ways we can look at the efficiency of stove is here's 3 different versions of stoves you might use to boil water. And the efficiency calculation would just be how much energy goes in compared to how much energy gets in the food, gets in the water that you're trying to cook. Let me describe these little stoves a bit. First, this is just a Coleman gas stove. It has just this very simple burner on top of a canister. When you turn the canister on and you light the flame, this little part, there's flame coming up through here, and you put a pot on top, and it works pretty well. And we can measure the amount of fuel in the canister before, the amount of fuel afterwards, and calculate the amount of energy that was in that fuel. This Provecho stove, or Stove Tech stove, it's bigger. This picture doesn't do it justice. It's about maybe a foot tall, where this canister is maybe 8 inches tall. And what it has is a metal-clad exterior around a ceramic interior. And when you want to have the fire going, you have these little sticks. See these little sticks here? And you stick those in. If you want to slow down the burn rate, you pull maybe 1 or 2 of the sticks out. If you want to have a faster burn rate, you stick them in, and you have really thin sticks that burn fast. And that it heats up the ceramic inside there, and then there's this little metal sheathing around here, and then there's the pot. And so that heat is very effectively transmitted to this pot. And this sort of stove is being used around the world to cook, and they're made locally in these countries off of designs that are provided by other people. And this stove is really good. I'm going to make a few comments on this in just a bit. And then here's a little stove that you might use for camping. It is very lightweight, stainless steel, double wall stainless steel cylinder. And what you do is inside you put a few little twigs and some paper or something to get it going. You light that, and then this little thing is a battery pack, and it runs a fan that draws air from the rim of the stove and re-injects that back into the bottom. And by doing that, provides oxygen for the fire, but also captures some of the gases that are coming off little twigs and sticks in there that are heated up and ready to burn. And this stove burns really fast and burns on very little fuel. So, comparing these across the efficiency, here's a cartoon of the energy flow. We have fire here. This is a really nice diagram I drew. And then you have to heat up the stove, and you have to heat up the pan, and then that heats the water. Well, each one of, you'd think, oh, we're just heating water, but each one of these steps is actually like our energy diagram. We have the energy source. How much heat is stored in the stove? How much does it take to heat up the stove? And for the stove tech, the one with ceramic, this takes quite a bit of heat to heat that up. But once it is heated, then you can keep it heated for a long time. Similarly, if you have to use a very heavy pan, it takes a while to heat up that pan. And then finally, how much is stored in the water. But there's this from the energy source to the stove to the pan to the water. So even just this very simple example shows that net energy of how much gets in the water. Now, a couple advantages and disadvantages each of these stoves. This one has very little mass that heats up, just this little burner part. This has a lot of mass and heats up, but once you get it going, you can keep it going for a long time. So for boiling water, this isn't so good, but for cooking a whole meal, it's very good. This is very lightweight, small, and efficient, but it's not very durable. You wouldn't want to have this fall off your table every couple days or something, and you need these little batteries to run it. So this is maybe good for camping or emergency use, but it's really, I wouldn't want to depend on this daily, whereas this stove here is really sort of a workhorse that you could just cook all day on, every day and do the work. All right, so let's talk now about optimization. And optimization is going back to that process efficiency. It's just, here's a simple example of what the process efficiency is. Here we have one part of the process that's constant, and maybe we have an increasing amount of machinery that supports another, either lower or higher rates. And when you match these up, this variable rate that you're of machinery that you're changing, there's one optimal ratio, and this is a type of optimization. Too little of the purple machinery slows the overall process. Too much is just wasted because you could have invested this in some other part. Now I'm going to take a little detour back to the types of efficiencies here and talk about the rebound effect that we studied in ESM 101, and I'm going to give a quick review of that. And the rebound effect is when you make something efficient, instead of the overall process becoming more efficient, often people will actually make more of something because it is so efficient. So our previous example is a good place to start with that. Let's say I have 10 units of this, and it's making 5 units of product per hour, and I have 10 units of this, and it's making 5 units of product per hour. And this, but remember, because there was a 2-to-1 ratio, just on our example, this is just an example, that we ended up with having too much of this machinery. So instead of slowing down and reaching efficiency of only making 2.5 units of product per time, I could invest more in machinery A. Now, if I come through here and I say, oh, I've got a really new efficient process for process A, maybe there's an electric motor and I have a way to save money by having more process A, then your overall winning approach for profitability of your company or running your farm is to invest in more of this. Double the amount of this and double the amount of product. So for not much more expenditure, you get double the product. So that's how the rebound effect actually works. Is you've got these multiple processes, And if one is limiting and you have a much more efficient solution for that, well then, boom, you just invest in there and you end up with making more of the product or using more resources in this case. So that's an example of how this overall efficiency leads to the rebound effect. It's not some sort of greedy thing. It's just sort of a natural outcome of increasing the efficiency of one of the processes in a multi-process operation. Now, there's a couple ways we can regulate processes and to reach the optimum. And one is you could just look at things and maybe turn the dial so that these processes match. But the other one is to have a dynamic dynamic optimization mechanism. So here's an example of that process we talked about before: process 1 and process 2. And what if one is too low and one is too high? What do you do? Well, if you're running an assembly line, maybe, or you've got a farm and you've got too many eggs and not enough milk, you increase one and decrease the other. But there's a way where this investment process, the logic of it, can be coded into an automatic process, automatic optimization. And that is, here you have process A and process B, and they lead to C. And when you have more C, and C could be, say, maybe profit. If process 1 is low, then you reinvest in process 1. If process 2 is low, you take some of this profits or whatever it is and reinvest it back in process 2. And if you set this up so that it happens automatically, then this dynamic optimization process just will keep going along, and everything will just keep growing. There'll be more and more process 1 and more process 2, and it is dynamically optimized. So we can make a systems model of this, and when we do that, the systems model, you would hope that you would get a smooth response for the investment in process 1 and process 2. But really often you see this sawtooth where it goes along for a while where process 1 is limiting, and then there's reinvestment in process 1, and then all of a sudden process 2 is limiting, and etc. You reinvest back and forth in these different processes as you go along. So that can be all right. It just depends on the time lag. But there is a possibility that if you're doing this in a variable environment, say like a fluctuating environment or oscillating environment, that the time lag could mean instead of optimizing for where you should be, you're always optimizing for where you were. You're chasing your tail. You're never optimal because you're always optimizing to the wrong criteria. So this is something that's a real concern in cybernetics and control of operations, and it really relates to this idea of optimization. Now just remember, a static process, just fixing a static process doesn't have this sort of control feature, and it may not be efficient, but you also don't want to have too much control so it just chases itself all the time. So there's this old story about that a broken clock is right 2 times a day. It's exactly right 2 times a day, and an operating clock may be never right. So you have to just think about it in those sense. You want something that behaves well. Okay, another point I want to make about regulation is that often we think of biological systems as being very well regulated. And so, for example, your body temperature is very well regulated, and often they compare that. I've seen this time and time again where people compare that. Oh, it's like a thermostat in your house. If you're too hot, the air conditioning kicks on, and it's too cold, it kicks off. Well, that's just way too simplistic to understand how it actually works, and there's this danger of having a metaphor that's overly simplistic and they actually take action based on how you think things work. So let's just take that example of human body temperature. If you are too hot, there's like 5 mechanisms with overlapping timescales. If you're too hot, your skin will flush and try to dump some of that heat. If that doesn't work, there'll be excess blood flow, especially to the limbs, to try to dump heat. You'll start sweating, but this is again individual. Some well-trained athletes, conditioned athletes, they'll start sweating as soon as they start working out, even before their body heats up, just because it's It's expected routine. Then, but for the rest of us, we'd start sweating after we were hot for a little bit, and then we'd start breathing more heavily. The breathing rate would go up to try to compensate. And finally, or anywhere along in this process, if you were uncomfortable enough, you might just move someplace in the shade or start fanning yourself or take off, unbutton your shirt or do something to cool yourself down. So my point here is that when we try to emulate these ecological processes and talk about efficiency and organic regulation, we really have to sort of understand the complexity of those natural regulation mechanisms to see that this is a tall task in order to have regulation over 5 different timescales working from different mechanisms just to meet the goal of maintaining a narrow range of body temperature. So one thing we can do is we can talk about how we might design things to be more efficient and build in that sort of optimization. So here's a couple good examples. In homes in the northern hemisphere, you can have south-facing eaves on the house, and during the sunny part of the day, in the summer, the windows will be in the shade. In the winter, the sun will come in. So this is a very simple design feature that you see in a lot of well-designed homes. Another example is a governor on a steam engine, that little whirligig thing that as it spins faster, it actually pulls up a little lever and slows down the amount of fuel that's going into or the amount of steam that's going into the steam engine. And then wind turbine blades, when you see they self-feather when the wind is too strong. Some of the larger wind turbine blades also are very they're very flexible, so if there's a little puff that comes along, they automatically dump that energy. And this again to avoid the damage in very high winds. So these designs actually give up some of that raw efficiency for the control. And anytime you see like a good design, it probably has this loss of just raw efficiency. So for example, if you want to heat your house the best in the summer and in the winter from the sun, you might have no eaves, so you catch all the light. Well, then during the summer, that's a bad plan. So, or if you wanted just the maximum output out of a steam engine, but maybe risking have it blow up every once in a while, you'd have that governor off and just like run it as fast as you can. That would get the most power output per the energy in. So these are examples of giving up some of that raw efficiency for control and building that in. And this is really what we want to be looking for. Okay, I have 2 more points, and they're not as technical as these ones we've been talking about up till now. One is when we are trying to optimize, and we're optimizing, say, for energy output in heating water or distance traveled and transportation, whatever. These are very simple output functions, but often we have to optimize between several different parameters. And just as an introduction to this, because we're going to come back and talk about the trade-off between water and energy and land, those sorts of things, especially with agriculture. If we have several objectives, and if we trade off one for the other just linearly, like the more we meet objective, in this case, let's start with objective 1, but the more we meet objective 2, we're always the same distance out here. We're always on this line. We can trade off, and the sort of sum of objective 1 plus objective 2 always stays the same, just a linear trade-off. Now, if we're lucky, we can find a synergistic system where as we meet objective 1, but then as we move out objective 2 for a while, there's a synergism, and both of them together give you more than just you'd expect to just added them up. This is a synergism of meeting objective 1 and objective 2. And in ESM 101, we talked about this with land use, that you're going to have parks that are near natural areas that are near, say, tree farms. The combination of those out here is much better than just all parks or all tree farms or, just all of one thing. You can actually get beneficial objectives from both of them. And then finally, the one we really need to worry about is this interference, where when we try to, if we have objective 1, any any progress we made toward meeting objective 2 has serious costs. And again, in ESM 101, we were talking about natural systems. This was, you can have a lot of people and no cougars, or you can have a lot of cougars and no people, but mixing cougars and people is sort of bad for both people and cougars. They don't get along very well. So we're going to come back to this idea about, because obviously we want to try to find situations that are synergistic. We also want to be worried about staying away from systems where when we try to optimize for one objective, we really interfere with other objectives. All right. Now, to the theme of this lecture is that efficiency and optimizations are not always how you solve problems. Sometimes, and I often hear this, people say, if all the effects are the same, we should just do things more efficiently. Well, that's true. I don't argue with that, but there's so few times when everything else, when all the other factors are the same. In fact, I can't think of any that aren't just trivial. So, like I told you, like transportation, people and cougars, where you put parks, all those things are multi-objective. So you can't just have make one thing more efficient without it impacting something else. I mean, remember one of the laws of the sort of pseudo laws of ecology is that everything is connected. So here's an example of, in particular, back at the original point about waste. Not all waste is the same. We can have waste in the production and use of lumber. Trees that fall on the forest floor because of the way we cut them down and stuff, that's one type of waste. You know, those regenerate, they can help the soil. Sawdust on the mill floor, that can be repackaged and made into heating pellets or some other processes that recapture some of the use of that. Defective wood products that have already shipped to the consumer and then have to be disposed of, like defective wood paneling and stuff, that's a very bad form of waste. It doesn't help anybody. It doesn't help the forest. Can't really be repackaged. Often it has to be disposed of as very sort of harmful waste. So making the process more efficient by decreasing the amount of waste, we could have a process that was very inefficient but left trees on the forest floor, but everything else was highly efficient. That'd be good. But we could also have a very efficient process, but the little bit of waste was this really defective wood product that was dangerous. That would be bad. So we need to understand what the type of waste is just as much as we need to understand what efficiency we're going for. Now, the progress and provenance. I mentioned this before, and I just want to come back in 101. I want to come back to it here. Our country, the United States, and Western countries seem to have a dedication to progress, almost religious. So unless we're moving forward, unless we're making advances, unless we're becoming more industrialized and using more technology, it's not worthwhile. And in ESM 101, we were talking about natural resources, and provenance is really the prudent care of this. But there's this belief in progress that more efficiency, more technology is always going to be good, and we really have to be careful about that. And this is a good time in the course to inject that, because it's almost religious. And if you want to see what I mean by that, you can. I'm sort of kidding here, but you can listen to this song by Brad Paisley where he's equating, he's singing Hallelujah to different technologies. But the idea here is that we need to decide, where we're going and what we want to do with this technology, as much as as just the fact that we are becoming more technological or more efficient. So this is a good time to mention resiliency again. Resiliency was the ability of a system, a society, or an economy to withstand shocks and come out in an improved way. So if you have good built-in control systems that manage the energy flow and the resource use in your society, and that they are as efficient as they can be, but they're not like chasing their tail, they're not adjusting to the wrong signals, but they're also sensitive to this idea of if there is a disturbance or a shock, it's gonna help improve and restore conditions. That's the sort of overall control that we need to be looking for. And this is very similar to health in a human. When you get sick, you recover, but also you might recover in a way that you're actually healthier than you were before, or you could stress your body through exercise, and actually when you recover from that stress, you're actually better than you were before. So this idea of being able to be resilient and recover to be able to handle those stresses, that's an idea that we want to have for general environmental systems, and we want to use technology and the efficiency and optimization of that technology to meet that goal. Finally, we often talk about, in this case I talk design for efficiency and optimization, but we can use policies to increase efficiency of human processes. And the question is, if humans are so adaptable, why can't we get them to act more sustainably? Why can't we design policies and equipment that are actually easier for people to do the right thing rather than be wasteful? And then, again, this underlying question about why doesn't education work better? We often say that, well, in order to get people to do things better, they just need to be more educated. Well, there's a fallacy there that I'm going to point out here. First of all, policies. The best policies that I think we have working for us are ones that just nudge people to make better decisions. They don't mandate one particular part. And there's a good book called Nudge by Thaler and Sunstein. And the idea is you set the default policy. If people don't make any changes in the policy, then it just ends up being better for the environment. But you provide them options. So, for example, the default could be, in a store, the default could be you bring your own bag, we won't charge you anything. If you need a paper bag or a plastic bag, we'll charge you for that. So it's really a policy, economic incentive, and it'll encourage people to bring their own bag. But if they don't, they can pay 5 cents and get a paper bag. You're just, you're neutral about that. You don't shame them and throw their stuff all over the floor and create a big panic about that. There's other things like in the built environment. There's a new book out by Wansink, and it's called Thin by Design, and he talks about how certain factors can get people to just eat less and eat more healthily. So again, we're talking about Americans that eat too much. One is smaller packages for snacks. People will actually pay more money per weight of snack if it's just small and packaged, and this is what their snack is going to be. And then the other thing is by design, like don't eat in the kitchen. Set it up so you have to eat at the table. Then if you're going to go for seconds, you're going to have to go all the way back in the kitchen. And maybe if you're just lazy, you'll just sit at the table and not eat anymore. And if you actually have to do something to get more food instead of just like eating out of the pan when you know when to stop. So this is examples, and again, they weren't very closely related to sustainability, but we can have examples like this that in the built environment, people do the right thing just because it's easier. And instead of trying to mandate particular behaviors or behaviors, then you would just try to build it into it. And finally, why isn't education more effective? Well, I'm going to give you just 3 points on this, and this could be a huge discussion. But first of all, we don't teach values in government-funded schools. We don't have this thing where we have kindergartners being indoctrinated into sustainability. That's just not part of what we do. And okay, you can imagine that's a huge discussion. We don't need to get into that. There has been some success in teaching adolescents to value nature. In Englehart's European Values Survey, they found that adolescents that were taken out into nature, into ecological places, they then, when they were adults, they would actually pay more money to have those sorts of green spaces around. So again, this is a long lag time, 10 to 15 years between the time somebody's an adolescent and becomes a voting taxpayer. But that, that's really sort of what it takes. It's not like just telling people in school you should pay more taxes. You got to get them out there. They have to experience and evaluate it. Now, finally, this is really the nail in the coffin for why education doesn't work. There's a and we're going to talk about this when I talk about worldviews, but educated and literate adults who are polarized politically actually diverge when they have more education. So in the case of do fossil fuels cause global climate change? You look at this. This was a project done by the Yale Cultural Cognition Project. This is their probability of they think what the correct response is to global climate change. Should we have more regulation or less? Liberal Democrats diverge from conservative Republicans, and it's hard to see this bottom, but this is the amount of their education and literacy on climate issues. So Democrats and Republicans are diverging. They're moving further apart with more education. They're not coming to some sort of agreement that, oh, well, you know, I'm a highly educated Republican and therefore I'm going to use the same sort of worldview skills as a highly educated liberal Democrat. So this again is just having more education is not the solution. And if you say, well, we need to educate them in a particular way, well, that's propaganda, so you can't really go there. So again, the hope for broader higher education to solve the problem is pretty weak unless we find other ways around it. And that's one of the things Yale Cultural Cognition Project is working on. You provide alternative solutions that they can get at, and we're going to talk about a few of those in one of the later lectures. So with that, I'd just like to summarize what we talked about today. We talked about definition of efficiency, how you can have two types of efficiency. And in the process, in the overall efficiency, you might optimize in a different way. Have to be careful about optimizing when we have multiple objectives because often they're at odds with each other. And finally, just going for efficiency is not the goal of society. Society wants to have resiliency and health of the systems, and we do that by building in good control mechanisms. All right, so that's a lot, and again, the main themes here are important to remember in this course.